The first construction is constant functor and identity functor. Both of these functors are also monads, and their applicative instance is following from their monad instance. Nevertheless, let's look at the code. The constant functor is a functor that takes a type parameter a and returns a unit type. So we could define it as this type function that takes a type parameter and returns always a unit type independently of the type parameter. So that's why it's a constant functor. It's like a constant type function. Now, for the constant functor, there's only one value that data can be if the data is of type f of a, namely the unit value. And so all methods of the functor, including monadic methods, flat map, pure, map, zip, they can only return the unit value. Since all methods return a unit value, all laws are trivially satisfied, because the laws say that one combination of methods should be equal to another combination, but all of these always return the unit value, so they're always equal. So in this case, it is trivial. We don't need to check any laws here. Let's consider the identity functor. It's a type function that takes a type parameter a and returns the same type a. So you can look at it as a type function that is the identity function at type level. Let's define this type constructor like this. Let's define the functor instance. It is a standard, very simple code that just applies the function f to the data. There is nothing else we could do. Let's look at the applicative instance. Now I defined this type class that I called woozip, which is just a type class that expresses the applicative property of the functor f by defining methods wrapped unit and zip. Now I made this type class require a type class constraint that the type constructor f should be a functor. I also defined a pure method because we can now, using the functor instance for f, we can define pure through wrapped unit. I also defined some convenience methods, such as getting the woozip evidence value of this type, getting the wrapped unit value for a given type constructor, so I can just write wu of f at any point. It's very quick to get the wrapped unit value. I also defined a converter to cat's applicative instance. Now in the cat's library, the applicative instance requires pure and app, but when you reason about the properties of applicative functors and when you check the laws, it's much easier to reason about functions zip and wrapped unit than about app and pure. And so they're equivalent, as we have seen, but it's much easier to reason about applicative functors in terms of zip and wrapped unit. So that's why I define this as an adapter, but I don't actually use the cat's applicative. I use my type class woozip instead. And I also define a syntax that allows me to say fa zip fb, which is shorter and easier to read, which is equivalent to this. It's slightly more verbose. To define a type class instance for woozip, it is required to have a functor type instance. And so that's why I will always define first a functor instance for a type constructor, and then a wzip instance. So how do we define a wzip instance? Well, we just need to define the wrapped unit, the w, and the zip. In this case, the wrapped unit is just unit. There's no structure that wraps here or anything, so it's just unit. So we have nothing else to do except write these functions like this, and we could have written them using the Curry-Howard library, implementing them automatically. Because this code is completely determined by the types. There's nothing else you can do, for example, in order to return a value of type a tuple AB, if you're given a value of A and the value of B. There's nothing else you can do except this. So you could just say implement here. Well, this is shorter than implement, it's the same. Let's check the laws. Now, the Associativity Law says that this combination, well, let's undo my changes to see what the code is, since we need to know. The zip of A and the result of the zip of FB and FC is just that, and the zip in the other order is this. So we need to show that these are equivalent. But this is exactly the definition of equivalence, which is rearrangement of nested tuples. So there is nothing else we need to do here to prove. And similarly, identity laws. They say that zip of wrapped unit and FA must be equivalent to FA. But wrapped unit is just unit, and zip is just a tuple. And so this is a tuple of unit and FA, and that should be equivalent to FA. But this is actually the definition of our equivalence. We have equivalence that could rearrange tuples when necessary, and also add or remove a unit in a tuple when necessary. So that's just a definition of our equivalence. So the laws are satisfied by definition, without much calculation here. Consider now the second construction. This is a product of two functors. So if two functors are applicative, then the product like this is a functor that is also applicative. Now the product construction is seen in pretty much every type class. In the functors, product of two functors is a functor. Monoids, product of two monads is a monad. Filterables, product of two filterables is a filterable. Same as for applicative. It's a product is always going to be a construction for every of these type classes. However, the sum or the disjunction is not a construction for applicative. So the disjunction of two applicative functors in general is not applicative, and also it wasn't so for monads. We will see examples shortly of non-applicative functors of this shape. So let's look at the code for construction 2. Now, we need to define the type constructor somehow. Now, we can't just say type f of A because we want G and H as parameters. The way around that is to use the syntax of the so-called kind projector in Scala, which I've been using in this tutorial. And this is the syntax that represents the type constructor that is the product of G and H. So it takes a type parameter and returns this type. So this is just a syntax for a type function written like this. And lambda is a keyword that the plugin defines. So first we need to implement the functor instance. Here it is. G is a functor, H is a functor, and then we define a functor of this. So we need to define just the functor instance for a product, which is a standard code that you take component by component. The first component of FA you map, and the second component of FA you map. And these maps, this is in G, and this is in H. So component by component, you define it. The same way we define the wrap unit and the zip. We define it component by component. So for example, zip should map things like this. And we can just take this and this together. It will be the first component of each of them. And then we take this and this together to zip, which will be the second component of each of them. It's like that. It's the first value and the second value. So the first component of the first value is zipped with the first component of the second value, and you get this, which is the first component of the result. So component by component, we define wrapped unit and zip. The wrapped unit is just a tuple of the two wrapped units for G and H, and zip is a tuple of two zips for G and H. So this is a zip for G, and this is a zip for H. The laws will hold separately in each part of the pair because the computations proceed in each part of the pair independently. So the first component of the result depends only on the first components of the data. The first component of the result only depends on the first component of the data, and so on for the second component. So it is kind of easy to understand that the laws will all hold very easily. Let's nevertheless take a look at how that can be written down. So let's write associativity. So a pair of GA-HA. So I assume GA is of type G of A and HA is of type H of A. So this will be of type F of A, when F is this type constructor. We don't use the name F here, but I used it in the slide. So if we first zip the first two together and then take the result and zip it with GCHC, so what does it give us? First we zip like this, the first two, and then we zip the result with the rest. Now, if we apply the definition, we need to zip the first component with the first component, so that will give you this. Now, I stopped writing parentheses here because this is the zip in the G functor, which is associative by assumption. We already assume that G and H have associativity. So I don't need to write parentheses like this. I don't have to write it like this. It doesn't matter if I write it like this or if I write it like this. The result is guaranteed to be the same already by associativity in the functor G. So also here in the functor H, I don't write the parentheses. And clearly, these expressions don't depend on the order in which we zip. So let's zip together the second two. And the result will be like this. We have this pair, and then we zip it with this GAHA. So again, we zip the first component with the second, with the first component, the second component with the second component, and the result is this. So we get exactly the same result after using associativity for G and H. So that proves the associativity law more vigorously. And the identity laws are proven similarly. We take the wrapped unit, which is defined like this by our code, and we zip it with some arbitrary GAHA, and the result is the zipping of wrapped unit in each component. So we assume that this is equivalent to just GAHA in each component, because the identity laws, as we assume, hold for G and H already. And so this shows equivalence that we need, namely that this is equivalent to this. And similarly, we can show the right identity law. The third construction is a free-pointed functor. I already talked about this in the previous chapter. Actually, this construction, as well as this one, are free constructions, which I will talk about in a later tutorial. For now, it's just a name that I'm using to remind myself of what it is. And for this tutorial, I'm just using this definition. This is a functor construction defined like this. I'm not going to use the fact that it is a free construction, because we haven't yet gone through this in the tutorials. So for the functor defined like this, assuming that G is applicative, we need to show that F is also applicative. So let's see how that works. So this is this functor. Again, we will use the kind projector in order to denote this type constructor. And so the syntax will be like this. So it's a type function that takes a type parameter A and returns a disjunction of either A or G of A. Note that in the syntax for the type function, A is a type parameter that is only defined in the argument of this type function. So this is not a type parameter here. It is not a type parameter of this function. It is a type parameter only of the type expression here. So that's important to keep in mind. So I could use a different letter here in principle, and it's not a type parameter in the value here. So the functor instance is standard. We take a function f from a to b, and we apply it to a here or to a here, depending on where we are in the disjunction. And if we are here, then we need to map it over the g functor. So this is a map in the g functor. So we certainly need to assume that g is a functor for this to work. But this is standard. Let's define the zip instance. So I have put here a type constraint so that they're both a zip and a functor. And this is just so that I could more easily use map on G if I ever need it. But it seems I don't really need it. So let me remove it from here. How do I define the wrapped unit and the zip? So that's actually an interesting question, because wrapped unit is required to be a value of type f of unit, which is either unit or g of unit. So we have two possibilities to implement this method. We could have the left of unit, which is this, or we could have the right of g of unit, which is a wrapped unit of g, which is this. So we could have either this or that. We actually don't know upfront which one is correct. We need to find out. So it turns out that only this fulfills the identity laws, and this one does not. We'll see why very shortly. But at the beginning you don't know, so you know that there are two possibilities. You should have to explore both of them. How do we define the zip method? Well, the zip needs to take either ag of a, either bg of b, and return either of this, ab, g of ab. So clearly we have several possibilities here. We can have a left-left, we can have a left-right, and so on. So let's match on all these possibilities. So we have 4 cases. If both are on the left, then we have a value of type A and a value of type B. What can we return? Well, we need to return a value of this type. So we could return a left of AB, like this, or we also could return a right of G of AB, where we could easily lift the pair AB into the functor G by using the pure method of the functor G. You can very easily just lift. So the question is, should we do that? Should we return this, or we return right of G pure of this? Turns out that we have to return this, otherwise the identity laws will not hold. We'll see why. Now, let's see what happens when we have a mixed term, left and the right. Now, in that case, we have an A and we have a G of B. What can we return? Well, we can't possibly return a pair of AB, because we don't have a B, we have a G of B. So we must return the right part of the disjunction. So we have to return right of G of AB. Now, clearly, we have to combine somehow A with G and B, and the way to get G of AB is to use zip on G, because that's the only thing we have. That seems to be the right way, but then we need to lift A into the functor G, and we have this. And this is actually, according to the identity law in the functor G, which should hold, this is equivalent to just F mapping, or mapping, over GB over a function that takes B and returns a pair AB. So let's just write it like this, because it's easier to understand what's happening. So similarly, if we have a right on the left, we must return the right of this combination, where we lift the B into the functor G and then zip together with GA. Finally, if we have both on the right, then we just zip them together, and they remain on the right. So you see, only when both of the data values are in the left part of the disjunction, only then we can return the left. In all other cases, we must return the right. So that's how it must be. Now, in my intuition, it would be already suspicious if we wanted to return right in all 4 cases. It means that somehow we are losing information. We're never returning a left, and that's going to lose information, and certainly that could be an obstacle to satisfying the laws. We'll see that indeed that is so. Let's check associativity. Now, to verify associativity, we could have just written FA, zip FB, zip FC, and substituted this code, but that would be very cumbersome, because there will be 8 cases to consider. It will be a lot of writing and work. Let's instead try to visualize how this operation zip works in this functor. And the way to verify associativity easier is to consider a zip of 3 values like this, with different parentheses, first in this way and then in that way. But try to define zip in such a way that it is manifestly independent of the way that you put parentheses. So try to reformulate how the zip is defined so that we can somehow define this operation directly for 3 elements rather than defining it only for 2. If we are able to define a zip operation directly for 3 elements like this, in a way that is clearly independent of where the parentheses are, in that A, B, and C all enter in the same way in this computation. There isn't any precedence. It's not that A and B are first and then C somehow. Then it will be manifestly associative. So let's see how that works in this case. So consider this situation. Now we could have all of them on the left, and then we would be in this situation. We would return the left after the first pair and also after the second zip, or in the other order, it would be exactly the same. So if all of them are on the left, then it's just going to be the result is just going to be this triple with parentheses here or with parentheses here, but that's equivalent according to our definition of equivalence. And so that's associative. So if they're all on the left, then this operation is associative. The result is manifestly associative. Now, if even just one of them is on the right, then we know that the full result is always going to be on the right. And we know that what will happen is that all the parts that are on the left, so maybe, for example, this is on the left, but this is on the right, and this is again on the left. All of those that are on the left are going to be lifted into the functor g using the pure operation. And so basically, you could imagine that first we lift all of these that are on the left into the pure, into the g functor, and then we have all of them on the right, as if, and then we just zip them together. So the result would be a zip in the g functor of 3 values from the g functor, and that's associative. So therefore, we have formulated the computation in a way that is manifestly associative. It's independent of the order of parentheses. And so in this way, we figure out that it's associative. It's much faster than to write out this code. Let's check the identity law. So the wrapped unit is on the left. It's a unit in the left part of the disjunction, which I denote like this in my short notation. Consider the right identity law, for example. So we have some FA, which is this type. We zip it with this. Now, if FA is on the left, then the result will be, according to our definition, this, which is going to be this. Left of A and the unit. And that's equivalent to left of A, according to our convention, because we can always add or remove units from the tuple. And so then the result is this, which is equivalent to that. So that's an the identity law. If FA is on the right, we need to lift this into the right and then zip with FA. When we lift unit into G using pure, the result is the wrapped unit, which is pure of unit. That's the definition of what the wrapped unit is. So in relation to the pure method. And so we have the zip equal to this right of this with a wrapped unit of G. Now the identity law for G tells us that this is equivalent to GA. Therefore, the result is equivalent to right of GA, which is exactly FA. So, in other words, zipping FA with this always gives you something equivalent to FA, and that's the identity law. And clearly, in the same way, we check their left identity law. Now, if we define the wrapped unit like this instead, then we can see that the identity law will be broken. Here's why. Consider the zip of a left value with this wrapped unit defined as the right of wrapped unit of G. According to our code, whenever something is on the right, the result is on the right. So the result of this is going to be right of something. Now, whatever we compute in here, we couldn't possibly reproduce a left of anything because it's already on the right. So it cannot be equivalent to a left of A. Our equivalence rules are that we can rearrange tuples and we can add or remove unit values from tuples. Our equivalence rules do not allow us to interchange anything else or to change at all anything else. So we could not change left into right. And so that's not going to be equivalent. And similarly here, if we define this to be right, then zipping left with anything could never give a left. And so the identity law would have no chance. And so in this way we see that this implementation is the only one that respects the laws. There are several implementations that are of the right type signatures, but only one implementation respects the laws. So that's an interesting situation which happens for this construction. Now, the next construction is the free monad over a functor G. So G here is an arbitrary functor. And this is a recursive type that's defined like this. Now we have seen in the previous chapter that this is a monad. And any monad is an applicative as well. We can define a zip function for a monad like this. And we can define pure. Monad already has pure, and we can define the wrapped unit as pure of one, pure of unit. So if we have a monad construction, then we already have the monad laws. The applicative laws are consequences of the monad laws when the zip and the pure are defined like this through flat map. So we don't actually need to check any laws here for this construction because we already checked the monad laws, and the applicative laws are a consequence when we define applicative instances through monadic instances. And the same holds for this construction. This construction was also a monadic construction, so we don't need to consider it separately in this chapter. Notice that we did have to provide proofs for these constructions because even though we had monadic constructions of the same form, those required, for instance, G and H both to be monads. And now we don't require this. We only require them to be applicatives. Similarly here, we only require this to be applicative. So we have relaxed some requirements as compared with the constructions in the monad chapter. And so since applicatives are a strict superset of monads, and we have relaxed those requirements, we have to provide a proof for these constructions that does not assume monads for these, that just assumes applicatives. And that's what we have done. We provided proofs of the applicative laws that only assumed that G and H satisfy applicative laws. We did not assume that G and H were monads. Now, in these two constructions, there aren't any constraints on G and H that we changed. These are exactly the same constructions with exactly the same conditions for G and H as in the monad constructions, and therefore we don't need to prove anything. They are exactly the same. These constructions are stronger than we need. They prove that these are monads, and it follows that these are also applicatives. But that's okay that they're stronger, and they prove more than we need in this chapter, but that's fine. Now, the takeaway is that these constructions also work for applicatives because they are monadic constructions. Now, here are some constructions that do not correspond to any monadic constructions. These are the last three. The construction 6 is a constant functor giving a monoid value. So it's a type Z, some type that we know is a monoid. It is not a monad, actually. We will see this shortly. So the type constructor is defined like this, and we don't want to define it as a type F because we want to keep this Z as a parameter. So we again use the kind projector and we write this kind of type constructor. A type function that takes type parameter A and returns the type Z independent of A. That's okay, that's quite fine. So as usual, first we define the functor instance. Now the functor instance is standard. There's just one remark that I'd like to make here, which is that this function f is not used in the map function. So the map function is supposed to take a value of type f of a and return a value of type f of b. But both f of a and f of b are just the type z. They don't depend on a and b. So we just take this z and we need to return a z. Well, we return the same thing. We can't do much else reasonably. And we can't use f because we don't have any a's to apply f to, and also we don't have any other thing that would apply to f, or any function that would consume this type. We don't have any of that. So there's no way where we could use f in the code of map. So we are losing information, but that's okay. So we're losing this f, but that's fine. Let's look at the applicative instance. The wrapped unit is a monoid empty value. Well, this seems to be reasonable. What else can we return? We need to return a value of type z, but we don't have any data to compute that. So the only value we can return is the empty value of the monoid. And the zip operation is just a monoid combination, monoid operation on fa and fb. And we could have defined it in the opposite order. They will still be valid. So this is an arbitrary choice, really. So why do the laws hold for this? It is because if you look at the applicative laws formulated like this, they look exactly like monoid laws, except that in the applicative laws, all of these are values with type parameters. So this is some f of a, this is some f of b, this is some f of c. However, if f is the constant functor, then all of these are just the same type z, and then this becomes exactly one-to-one monoid laws. There aren't any more type transformations here. This becomes equality, and these three laws become exactly the monoid laws. So therefore this operation instead of zip exactly satisfies all the laws. And if we interchange B and A, it would be exactly the same laws with B and A interchanged where appropriate. So this will be exactly equivalent. Let us see why this type constructor cannot be a monad. So we could define the pure function by again returning monoid empty. There's nothing else we can return because we can't use a value of type A to compute a monoid value of type Z. So we could implement pure like this. We could implement flat map by again returning this FA unmodified. Now we can't use F at all, just like we couldn't use it in the map. So we're losing information in this function. We could also return here an empty value of the monoid. Or we could return this value. But in any case, we would have to lose information about the function f. Now, the left identity law for monad is this, which is a flat map with f, which is applied to pure, should be f. But flat map loses all information about f, as we have just seen. So this can't possibly recover f. Whatever you compute here, however you define pure, you cannot possibly recover f from a function that ignores its argument f. And so this law could not possibly hold. And it could not hold however you define this. You could define it in this way, or you could define it as z dot empty, but still you could not recover f, and this law would not hold. So the only constant functor that is a monad is this functor, is the unit. Because then you're losing information, but there's no information to lose. There's only the unit value. There's nothing else that you could possibly return, and so you aren't actually losing any information because there wasn't any information to lose to begin with. So for this reason, this is a construction that does not correspond to a monadic construction. The next construction also doesn't. It's similar to this one, except we're having here, instead of the A, we have the monoid Z. Now, G must be applicative, just like here. So why is this construction not monadic? Because even if you take for G the simplest functor, for example, this one, the constant functor, then you would have Z plus 1, which is a monoid, but not a monad, as we just have seen. The only constant functor that is a monad is this, the unit. So this is going to be not a unit, it's going to be Z plus unit. And so it's not going to be a monad. So it is impossible to have a construction like this for monads, where even if we require that G is a monad, still this is not going to be a monad for all G that are monads. Let's see how this construction works for applicative functors. So first we define the functor instance, which is standard. We just apply a function f to A under G using the map, or if we're in the left, we don't apply it. It's the Z value remains unchanged. So that's the standard implementation of the functor instance. So let's now look at the construction. So again, I have put here perhaps a constraint that I don't need. Now, we need to define a wrapped unit, which is of this type. And we have, again, just like in the other construction, we have two possibilities. We could return a left of the empty monoid value, like this, or we could return a right of the wrapped unit of G. So it turns out in this case that the correct way is to return the right, and the left of monoid of empty breaks the identity laws. We'll see why. Define the zip. Again, we need to match on the four cases. In the left, we just use the monoid operation to add together two values of the monoid. Now let's look at what happens when we have the cross term. So a z on fa is on the left, is a z, but fb is on the right. Now, we have a value of type g of b, and we have a value of type z. We're supposed to return this. We're supposed to return either of z and g of b. Can we return this? No, because we don't have an a. We have a z, and we have g of b. We can't possibly get an a from anywhere, so we can't possibly return g of ab. Therefore, we must return left, and left has only z in it, so we must return left of this z, and we must ignore whatever was on the right. Similarly in the other case. And only when both are on the right, then we can zip them together using the zip in the G functor. So in this case, it seems we don't have much choice about how to implement zip. We still have a choice about implementing wrapped unit. Let's check the laws and see how that works. So again, we will just do a consideration that zips together three values and formulates the result in a way that is manifestly associative. So consider these values. If at least some of these three are on the left, then according to our code, the result is going to be on the left. And we're going to ignore everything that's on the right. So therefore, we will obtain a result which is going to be a monoidal operation on all of the z's that are on the left, ignoring everything that's on the right. We could have 3 z's, 2 z's, or 1 z, but that's all. So that's obviously associative, because it doesn't depend on the order of parentheses, and because z is a monoid. And so this operation is associative in the monoid. Now, the other case is that we have all of these three on the right. In that case, the result is the right of the zipping of these three, which is associative, because by assumption, zip is associative in the functor G. So we have reformulated this computation in a way that is manifestly associative. The wrapped unit, we need to make a short computation here. So for example, we have this, zipping it with that. If this is on the left, the result is again the left, which is exactly the same. And so that's identity law. If we have GA on the right, and we're zipping it with this, then we're zipping this GA with the wrapped unit, which is equivalent to GA by assumption, since the identity law holds for G. So we have again right of GA, which is equivalent to right of GA. In both cases, the identity law holds. And the same way we check the left identity law. Now, if we define the wrapped unit as a left side of the disjunction, then we consider a zipping of left and right. And the result must be on the left, because anything that has at least one of them on the left returns a left. And therefore, it cannot possibly be equivalent to a right of GA, because whatever you compute It's going to be left of something, and it's not going to be right of GA. So that breaks the identity law. So in this way, we find that this is the only correct definition for the wrapped unit. Finally, the construction 8 is functor composition. When G and H are both applicative functors, then their composition is, which is G of H of A, is again an applicative functor. Now this is not a monadic construction because composition of two monads is not necessarily a monad. It may be or may not be in some cases, so it is not guaranteed. Whereas with applicatives, it is guaranteed. We will see an example explicitly in this tutorial where you have a composition of monads and the composition is not a monad. But you couldn't get such an example for applicatives. Let's see how that works. So we have two functors. We define their composition, which is defined like this, as a type function. And then we define a map, which is standard. We just map over H under G. So we have this nested map. Now let's define the zip. So how do we define the zip? We need to define a transformation like this. We need to define also the wrapped unit. So the only way to define a wrapped unit is to do first to take the wrapped unit of H and then lift it into G by using the pure from G. So that's the only way we could get a value of this type. The definition of zip is straightforward. We first zip the two G's together using the zip in the G functor. The result is a G of the product HA and HB. And then we map under the function, the functor G, we map HA and HB into H of A times B, which is this function, which uses the zip in the H. Let's check the laws for these. So this I simplified, and let me finish that. Yes. So let's check the associativity. The definition is like this. I'll just going to rewrite it a little shorter because it's easier to reason about when notation is shorter. Once we have the zip, we map that with essentially zip in the H functor. And when we have three values, GHA, GHB, GHC, and we zip them like this, then this is the result. Now, in order to simplify this, we use Naturality Law for zip. The Naturality Law says that for this zip, if one of its arguments has a map working on it, we could put this map over here and work on the first type inside the zip, leaving the second type unchanged. So that's a naturality law. Let's remind ourselves of the naturality law. See where that is. It's here. if we have a zip that on which some function works on the argument, then we could pull this out, and we have a zip of those things without anything acting on it, but we can act on the result of zip by the product of functions. So that's maybe okay. Maybe it's a little easier to see here. So zip, yes. So zip on which some functions have worked is equivalent to zip followed by some map. So we will do that. And we will pull this outside. So how do we pull it outside? Well, the result is that we still have this back here, but before that we have this map of zip h, which takes the first two. It's a product of two functions, one being zip h and the other is identity. So this is unchanged, and zip h is now acting on these two, because it was acting on these two. So I'm just using the shorthand. Let me describe it. It's the same as map of case HA, HB, HA, zip H, HB. So this map of zip H here, it was like this, but now we need to apply this to the result of zip, which is going to be of type G of H of AB, G of HA times HB and HC. So then HC needs to be outside of this tuple. So that is the result. Now we can combine these two maps together using the function composition law. Just we take this, we first compute this, and we match on that with this case, and we have this result. Now, obviously, this is a associative combination for zip H, where we could omit parentheses. And so when we do the same computation for this expression, we get a similar function with parentheses in the other place. And if we compare these two, we see that these are equivalent because the G functor satisfies associativity, and these are equivalent because the H functor satisfies associativity, and these are just equivalent by definition. And so we have found that the equivalence holds. The identity law is satisfied as well in the same way. We do a zip with map. We use the identity law for zip in the G functor. First, the identity law says that this is equal to gha.map of this function. And then we just add zip h on top. Now this becomes the zip h of wrapped unit h, which is equivalent to HA. So this becomes HA to HA. This becomes identity function. So mapping with identity function does not change the result. So therefore, zipping GHA with wrapped unit is equivalent to GHA. Similarly, we can check the right identity laws. So these are the constructions that I was able to find that build new applicative functors out of old ones. Now, I would like to give another example of an applicative functor that disagrees with its monad. So what does it mean exactly? Well, this is typically a situation when you have a functor that has a monad instance and also it has an applicative instance. And sometimes you would like the applicative instance to do something different than what a monad's definition would do. We have seen this in the first part of the tutorial, where you would have an either monad, which stops after the first error, but you can define an applicative on either that accumulates all errors. So this is an example of applicative that disagrees with its monad. It's often the case that you want monads to agree with applicative, but sometimes you want them to disagree. And here's an interesting example of a type constructor where it is easy to see that it's really reasonable for them to disagree. This type constructor is basically a lazy list. So I will explain what that means. If you delete this function from unit to that, then you would have a definition of a list. It's a recursive definition of the list functor. Adding this function arrow means that elements of the list are not yet computed necessarily. You could compute them by calling this function. You can always call it. It doesn't require any extra data, just a unit value, which you always have. So you can always call this function and get the next element and the tail of the list, on which you can again call this function and get again next elements. And maybe some computations could be encoded in this way, where maybe it's expensive to compute these elements, and this is only done when you want them. So in this sense, it's a lazy list. It does not have all its elements already evaluated. It's waiting until you need them. And when you need them, you call this function, and you get your next element. So let's see how we define this lazy list as applicative functor. This is the short type notation that we have just seen. And since this is a recursive type, we cannot use the kind projector. We have to use a class. Also cannot use a type alias. We have to use a class to define it in Scala. So let's do that. And I'm just using a very direct encoding of this type. So it's either unit or a function from unit to this. Now, in Scala, this syntax does not actually mean a function with unit argument. It's a function with no arguments, with an empty list of arguments. Scala has this syntax. It doesn't really change anything for us. Just a little less typing. If we wanted to have a function with unit argument, it would be like this. Just more typing for no gain in particular. Let's define some utility functions so that we can easily work with data of this type. First, let's do an empty list, which is just returning this first unit, which is left of unit. Let's define a function that takes an ordinary list and creates this lazy list. It would be useful for testing. The idea is that we would create f with a right, which would have a function that will return a tuple of the first element and the rest. The rest will be again f of right and again a function will be the second element, and so on. And finally it would be an empty list. So that's easily done. We match on the list. If it's empty, we return the empty, which we defined here. If it's not empty, we match on head and tail. We return a f with a right inside and a function like this, which will return a tuple of head and again a value of type f of a, which is a result of applying the same function list to the tail of the list. So that is easily tested now. We can create a value like this. And in order to get anything out of those lazy lists, we need to actually call the function. So this fetches all those things and calls the function. And the result is that you have a tuple with one element, which was a, and the rest, which is again the same story. Again, we have to do this in order to get anything out of it. So let's, for convenience, convert to ordinary lists. So that's how we convert. Straightforward function that would call and then call itself again. So these functions are not tail recursive, just using it for tests right now. So these tests check that indeed these lists work. Let's define a functor instance. That is straightforward because it's just a function, so we need to create a new function where we replace arguments and do a map recursively. And let's create a WZIP instance, an applicative instance. And that's where the interesting things happen. So first question is, what is the wrapped unit? Now, we could, in principle, return a left, or we could return a right, because the type has an either. So we could return a left, or we could return a right. If we return the left, then it will be just an empty list. So the wrapped unit would be an empty list of type unit. If we return a right, then we could return a function that has this a, which is a unit, and then again returns the same wrapped unit. That's what we do, in fact. It's a recursive definition that, in effect, it is equivalent to a never-ending sequence of unit values in the list. Because the list is lazy, it doesn't actually evaluate infinitely many elements. But if you request a next element, if you evaluate this function, then you would get again the same function that would generate the rest of the list. So the rest of the list is exactly the same as the list itself. And so, in other words, it's a never-ending sequence. It's not actually an infinite sequence in memory, of course. It's conceptually equivalent to infinite sequence, because you can request next elements as many times as you want. You will still have always next elements, the same element, which is empty. So converting this to list would be a stack overflow or a memory over out of memory error if you fix the stack overflow first. Now the zip operation is interesting, but it's really trivial in a sense, because if one of them is empty, we return empty. And if we have two functions, so GA and GB are functions of this type, and we again return a function which just has the tuple of the two first elements and then zipping the rest recursively. So this is a typical implementation of a zip of two lists, except that we need to dance around with these function calls. We have these functions and we need to match in a different way and so on. But other than that, it's the same. And so zipping a list of 2 elements with a list of 3 elements cuts this list of 3 elements to length 2 and gives you this as a result. So this is a standard behavior of the zip method on lists. But also this wrapped unit acts as a unit. If you zip it with some list, the result is the same as the initial list after the equivalence transformation. So how does it work? Well, since the wrapped unit logically represents an never-ending list or unterminated sequence, and this list is finite, the zip function will cut the longer sequence, because that's the code. If one of them is on the left, which is an empty list, then the result is an empty list. So whenever we get an empty list, we cut. And so that's going to be the result. Indeed, a zip defined in this way can't do much more than cut, because if it didn't cut, it would have to produce here another element of type string unit. But there's no string to get to write here. Logically, you would have to cut. Certainly in some applications this is not what you want, but in many applications that's what you want. You want to cut the longer list. And you could, conceivably, you could do other things, but what if the first list is empty? What do you do? There aren't any values for you to fill. You have to cut. And so, however, if you use the list monad, the definition of pure is not the same. It is not an infinite sequence. It is a sequence of length 1. So the pure would be just this. It would be an one-element list. And the standard zip function, zipping with this, would certainly not do what you want. It would cut at length 1. Now, certainly, if you define zip through the monad instance and not in this way, then you would have a very different behavior. And then, of course, the laws will hold. This zip defined from the monad will take each element from the first list and each element from the second list and put all those pairs as a resulting list. So, for example, zip of list of 1, 2, list of 10, 20. It would be a list of 110, 120, 210, 220. So certainly this is very far from the standard function zip on lists. It could be reasonable for some applications, but the standard zip function doesn't do this, it does that. And therefore, for the standard zip function, the correct wrapped unit is this infinite sequence and not this. And so this is an example where the standard zip function, which suggests an applicative, disagrees with the monad, which is also standard for lists, a standard flat map. It disagrees with that. And so that's, but actually they're both useful in different contexts. So this is exactly the kind of example I was talking about. And the reason that this disagreement might be troublesome is that if you defined for example, code that has a for yield construction, then you might be able to simplify it using zip. What if you notice that you have this kind of construction? And you say, oh, this is obviously a map2. This is a map2, or this is a zip, like this would be a zip, and this would be a map2. And then you would be tempted to refactor this code by doing something like this. But if the zip implementation disagrees with the monad instance, then you would have changed the functionality. You cannot replace this code with this code unless the applicative instance defines map2 in the way that is exactly the same as what would follow from flat map. Now, if you're using a type constructor for which the monad instance and the applicative instance disagree, then you should never refactor code like this. But you might be tempted to, or you might just do it without thinking. It's very confusing that these things are not the same. And so it is recommended, therefore, to avoid these situations and not to define applicative instances that disagree with monad instances. If you need that, the easiest way out is to rename the type constructor to some other name, have an alias or some different type that would only have the applicative instance but not a monad instance. And the first type would be a monad, and you would only use the first type when you use as a monad, and the second when you use as applicative. So that in this way you avoid potential for bugs that would come out of this kind of confusion. So finally, let's look at some examples of non-applicative functors. So these are the examples. Now, the first example is the disjunction of two reader monads, essentially. So reader monad, of course, is applicative. Also, it is this construction. But their disjunction is, in general, not applicative. Another example of not applicative is this. This is a functor in A, because A is here in a covariant position. See, this is to the left of the function arrow, so this entire group is contravariant in the contravariant position, but inside it A is also in the contravariant position, so that cancels out, and the result A is covariant here. Similarly here, A is covariant, and also A is here covariant. It's to the right of the function arrow. So these are functors, but they're not applicative. Let's see how we can verify that. So I defined these type constructors. I also defined this G, which is, I've just reversed these two errors. The result is that it's a contrafunctor. It's not a functor anymore, but it's very similar in structure. So now these are our three examples, F, H, and K. I'm going to try to implement the zip function using the Curry-Howard library. So I'm going to ask the Curry-Howard library to implement any code that has this type signature. And this is the all of type method. So I'm going to find all of these, so that the result is going to be a sequence of implementations. And then I'm going to look at those sequences. So This is all happening at compile time, so these tests run. Now, the length of zip_f is 1, which means that there is one implementation of this function, which is this type. But when we look at the code, which is printed in a short notation, you see that the code is that this function returns always none, so it always returns an empty option. A zip function that always returns an empty option is obviously going to violate laws, for instance, identity laws. Well, it won't violate associativity because it always returns the same thing, but it's going to violate identity laws that require it to preserve information. And since the identity laws say that zip of something with the wrapped unit must not change the something, so it should not lose any information. If zip loses information, then it's certainly going to violate the identity laws, and so the only implementation we have of this type signature, which is the zip type signature for this functor, is going to violate identity laws, and so there is no good implementation. And for these other functors, there's not a single implementation at all of this type. So those types could not be instantiated, could not be implemented by any code. So there's no code that's generic in all these parameters that implements this type signature, and also this type signature. But for the G, there are actually two implementations. So G is a contrafunctor. I just took this and I reversed the arrows. And it turns out there are two implementations. So that's interesting. And so let's look at contrafunctors now. All applicative functor laws that are formulated via a zip and wrapped unit actually don't use the map function. So we can formulate the same laws for contrafunctors. So we can say an applicative contrafunctor is a contrafunctor that has a zip and wrapped unit methods with the same type signature and the same laws, identity laws, law and associativity law. So that's the definition. So we will look at constructions shortly. But one thing we need to keep in mind is that contrafunctors are different from functors in that they don't have map, they have contramap. So, for instance, you cannot take a wrapped unit and map it to get a pure out of it because you don't have a map, you have a contramap. And so it's slightly different. Another thing is that we always have a function like this. Just drop B and take the first element out of a tuple. If you contramap with this function of CA, then you get C of AB, because that goes in the opposite direction. So CA with this function goes from here to here into CAB, which looks like what you want to implement the zip. You take the CA, you just contramap it, and you get CAB. But that's invalid as an implementation of zip, because it loses information about CB. And we know that would violate the left identity law. If you put identity here, you should reproduce CB on the right-hand side, but you lost all information about it. So naturality must hold, but with contramap instead of map. So that's another difference. Now, if you try to contramap this with a function from 1 to a, you can't. It's the wrong direction. You can contramap it with a function from a to 1, and you get c of a for any a. So that's different from pure, but it can be seen as an analog. Pure has a type signature a going to fa. This does not have a going to anything. You don't, well, you could imagine that you have it, but you don't use that information. So you don't use any values of type A to create this. You already can create them. So that's yet another difference. And also, there is no contra app. Sorry, where am I? There's no analog of app for contrafunctors. So these are the contrafunctors, and indeed we will see that this is one of the constructions, that the disjunction of two applicative contrafunctors is again applicative. This is this construction, which we will look at shortly. So, all right. So now we verified using the Curry-Howard library that these functors are not applicative by trying to implement the type signature of zip and finding in this way that for this functor there's one implementation of this type signature, but it loses information, and so it could not possibly satisfy laws. And for these two types, we found that there aren't any implementations at all of the type signature of zip. Now, I should comment here that actually it's quite difficult to prove that there are no implementations of zip. It's actually quite difficult to prove. So I'm using the Curry-Howard library that performs exhaustive search of possible implementations, but certainly it's not really a proof. I'm just running some code. Maybe it has bugs. So it's hard to actually produce a proof, and I'm not going to do it. If you go back to the Curry-Howard correspondence tutorial, you will see that this is equivalent to finding a proof in the constructive logic, or showing that there is no proof. So there are methods for showing that there is no proof. Proof theory gives you tools for doing this, but it is difficult and cumbersome. And so that's why I'm using the Curry-Howard library, in which I have a certain degree of confidence, where I can just ask it how many implementations a given type signature has. So having finished with constructions, we notice that some of them contain monoids. So monoids seem to play an important role. They're very similar to applicative functors in some interesting ways. So let's actually ask, what are monoid types? So what are the types that I could use here in this construction? The answer is, surprisingly, in Scala, any type is a monoid. All non-parameterized exponential polynomial types are monoids. What does it mean? We have monoid constructions in the previous chapter, and I could have made this observation already in the previous chapter, that these three constructions give new monoids out of previous ones, and also that all the primitive types, integers, floating points, and so on, sequences, and strings, and unit, all of these types have at least one way in which they can be implemented as monoids, as instances of the monoid type class. For instance, these are all like numbers. They can be added together, and that's a monoidal operation. These are all like sets, where you can have a union of two sets. So here is a sequence, a union is just concatenation, and this is a set union, and this is a map merging union. But basically, they're set-like, they're monoids, and strings can be concatenated because they're equivalent to sequence of integers, and unit is a trivial monoid. And case classes you can define using these constructions, and function types you can define using this construction. So a function from, say, float to a sequence of strings. It's just one of these constructions applied to one of these types. And so they're monoids. So all exponential polynomial types, that is, all types constructed from these three operations, starting from the primitive types, are going to be always monoids, at least in one way, sometimes in more than one way. So here's an example. Consider this type expression. In Scala code, this would be implemented as a seal trait with three case classes, because there are three parts of the disjunction. This is a monoid. I don't have to worry about how to implement it because I have these constructions. And once I decompose this into some of these constructions, starting from primitive types, I can just generate the monoid instance automatically or mechanically. Notice that this does not have any type parameters. If I have type parameters, then I don't know if that type is a monoid. I don't know how to implement a monoid instance for it. Maybe it will be a monoid when this type expression is actually used in my code, but I don't know that, so I don't know how to implement. And here's an example of a non-monoid type with type parameters. So if this were A to A, that would be already a monoid. It's a function monoid with function composition. But here I cannot compose two functions of type A to B and get a third function, again, of type A to B. No way. I don't know how to combine A's. I don't know how to combine B's. They're unknown types. If I knew that they were monoids, that at least B, if I knew that B is a monoid, that's enough already. I have this construction. But I don't know that. I don't know how to combine. So that is to say, all types that don't have type parameters and are exponential polynomial, such as this one, they're all monoids. So it is in this sense that I say all non-parameterized exponential polynomial types are monoids. A very interesting conclusion follows from it, namely that constructions 1, 2, 6, and 7 give us a way of expressing all polynomial functors with monoidal coefficients as applicative functors. Starting from monoids, we can build an applicative instance for any polynomial functor. So how to do that? The short summary of this construction is that we need to rewrite the polynomial in this form, which we always can do isomorphically. We can transform the type into this form, just like in school algebra. This form is called Horner's scheme for polynomials. So A is the argument and Z's are coefficients. In school algebra, they would be numbers, constants. And this is the variable in the polynomial. And so because we can write it like this, these are just a sequence of constructions that you apply, and you get an applicative functor. So let's see how that works. Suppose you have a polynomial functor, and which you can write in a short type notation like this. You have some coefficient that is constant type. Could be complicated, but it's constant. It could be like this, but it does not have type parameters. It's a constant type multiplied by some number of a's, or some power of a, but a fixed number. Then another monoidal coefficient. So we assume they're all monoids, these z and y, because they are of this kind, so they do not have type parameters. We can start with the highest power of the polynomial, like we do in school algebra, then some smaller power, and then finally we go down to power 1 and 0 with some constant types here. So this is one way of writing a polynomial, which we can always do. Another way would be then to put parentheses in like this. So starting from the lowest power, we take a out of parentheses and then factor it out. The result is a polynomial of lower power, which we can again factor out in the same way. And finally, in the middle of it, there will be some last a and z. And the z is the coefficient at the highest power of the polynomial. So we can always transform the polynomial into this shape, into Horner scheme. And notice here some steps could contain more than one a. So for example, it could be like this, because some coefficients could be 0, conceptually speaking, or 0 type as also something we could use here for generality, but we don't have to. Each of these steps corresponds to construction 7, which is this, z plus some g of a, actually, I think it was called. And construction 2, which is multiplying a and g of a, where g is already applicative, and a and z can be then used like this. You can add z, or you can multiply by a, and that's still applicative. These are the constructions. Construction 2 and construction 7. So indeed, we can find that it is applicative. But how does the applicative instance actually operate? So what does the applicative method, wrapped unit, for example, do, or zip? What do they do to types like this? How can we visualize those things? So here is how. The wrapped unit for construction 7 is this, we have found. And the wrapped unit for construction 2 is this. And so the wrapped unit for the entire polynomial is going to be, every time you step through construction 7, you discard the z, so you go to the right, like this. In other words, every time in construction 7, when you go, you discard this, then you keep a, you discard this, you keep a, discard that, keep a, discard that, keep a, and finally you're here. So you have discarded everything but z, a, 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 a. In other words, everything but the term of the highest power of the polynomial. So therefore, the wrapped unit for f of a is of this form, is the highest power term of the polynomial, where you take, instead of z, the unit value or empty value of the monoid, and instead of A you put the unit values, so that is going to be the wrapped unit. Let's look at how zip is defined. So it would be good if we visualize, for example, zip of these two terms. Then if we can do it, then since zip is distributive, well, zip of this and some other polynomial essentially is just one zip of this kind, because a value of this type must be in one of the parts of the disjunction. So it's one of these. Well, it's either this or maybe it's this. So it's sufficient to be able to compute zip for two monomials like this. So let's see. So construction 7 says that the result of these is of type RAA, because construction 7 says if one of them is on the left, we discard what is on the right. In other words, if we are here, for example, we discard this. So if two polynomials are zipped together, we discard the one that has higher power. So we discard this S. We discard the power. So we discard the coefficient at the higher power, and the result is the coefficient of the lower power that remains. And we need to discard, so we will go through these, and we will discard as many of these B's as we need to in order to have a pair for each A. So in other words, we'll discard B3 and B4 here, and we'll keep B1, B2. Actually, it might be that we discard B1, B2 and we keep B3, B4. That could be an equivalent definition. Doesn't matter right now. We just want to understand the principle. So the principle is, first of all, we choose the polynomial of the lower of the two powers. We discard the monoidal value of the other one, and we discard the extra values that cannot be paired up with ours, because we need to zip those together, and we return this. So we treat them as lists, and we zip them together as lists, so we cut the longer list when we do that, and we discard the coefficient at the longer list also. We keep the coefficient at the shorter list. If the two lists are of the same length, we don't discard this. We use the monoidal operation on the coefficients, and we just zip the lists as before. So in this way, we can visualize how constructions 2 and 7, as well as constructions 1 and 6, as far as I remember correctly, if I'm wrong. Yes, because we need a constant functor sometimes, we need an identity functor sometimes, and we need these two constructions. So in this way, we have defined how they work through constructions, and we have visualized how they actually work on specific terms of these types. So that certainly is plausible, that you could take any polynomial functor and more or less mechanically transform it into this way, into this form, check that all of the coefficients are monoids, and then generate the monoidal instance for each of them, and then generate the applicative instance for FA. Here are examples of polynomial functors that are applicative because they're polynomial. So the first example is interesting because this type constructor cannot be defined as a monad, cannot have a monad instance. You can define the methods pure and flat map with the right type signatures, but they will not satisfy the laws. There will not be associativity and identity laws for satisfied, no matter how you try. Several people have verified this by explicit calculations. But it is applicative, so the applicative instance is very easy, and it's just this construction of adding z to an applicative functor, which is a product of two identity functors. So obviously this is an applicative functor. Also, it's interesting to look at this as a composition of two functors. One option, so 1 plus something is option, and then a functor which is the pair AA. So that's clearly a polynomial functor. So the composition of option of pair AA is not a monad. But option by itself is a monad, and pair AA by itself is also a monad. So this is an example where composition of two monads is not a monad. The composition in the opposite order will be a monad, a pair of two monads, 1 plus A times 1 plus A. That is a monad, but not composition in this order. And this example is just a polynomial, is just to visualize what I mean by a polynomial with monoidal coefficients. It's like a polynomial, but the coefficients must be monoid. So any types that have no parameter a in them, so like the z, it must be a monoid. Now this is a monad. This functor, I believe, is a monad, but it's not obvious how. You need to find monad constructions that, for example, you have here a writer monad, obviously, and then you have a plus, so you multiply identity with the writer monad, so that is a product construction for monads, and then you add a, that's a free-pointed construction, and that's also a monad. So through finding a sequence of constructions starting with a writer monad, which we know is a monad, we can show that this is a monad without explicitly having to prove that laws hold. And notice that our examples of non-applicative functors were all non-polynomial, so they all had function in them. So they're not polynomial functors. Indeed, there aren't any examples of polynomial but not applicative functors that have no type parameters and only monoidal coefficients. It's very easy to drop in something like this and say, oh, this is not monoidal, and if I have a coefficient like this, then obviously I don't have applicative functors. So that's certainly would be an example. So polynomial functor with non-monoidal coefficients. Not very interesting, perhaps, but still, it's a valid example. So let's continue and take a look at contrafunctor constructions. I already described how contrafunctors are defined. So in the next and final portion of part 2 of chapter 8, I will talk about the applicative contrafunctor constructions, as well as profunctors and applicative profunctor constructions.